Let's finish up section 3.9 with a conversation about antiderivatives and motion. And we have three big ideas with motion. The first one is displacement. And think of displacement as this. Displacement is where you are. So if we have some sort of path here, then where you're located is your displacement. And usually where you're located in reference to some starting spot. So you could be displaced plus 1 unit to the right, or you could be displaced to the left, and they would call negative 1 unit. So displacement is like distance from zero, except displacement can have positive and negative values. So you can be displaced backwards or displaced forwards. And so displacement is like distance, it's where you are, but it's where you are with both positive and negative possibilities. Similarly, velocity is how quickly you're moving in either direction. So it's how much you're being displaced. And velocity, just like displacement, can have a positive velocity or you can have a negative velocity. So if you're moving in the positive direction, your velocity is positive. If you're moving negative backwards, your velocity is negative. So velocity and speed, right? So speed is the version of velocity that doesn't have positive or negative. Speed is always positive. So think of displacement and distance as the same relationship as velocity and speed. And then finally, acceleration is how much your velocity is changing. And we usually think of acceleration as having both positive and negative possibilities as well. Well, okay, we kind of already thought about this a little bit, but let's just recap what we've said before. Well, if you have the distance and you want to get to velocity, how do we get here? Well, we get here by taking a derivative. So if I know my displacement, I want to get to the velocity, I take a derivative. And if I know my velocity and I want to get to acceleration, I take another derivative. So basically, to go from displacement to velocity to acceleration, I take derivatives. And in fact, there's actually more after this. So if I took another one, usually after acceleration, we call that the jerk. And that's how much the acceleration is changing. And you could think of this like if you get slammed by another car, your acceleration changes quickly, there's a big bump in the car, and that's what causes whiplash and things like that in accidents. So we usually call that the jerk, but we're not going to make a big deal of that right now. Okay, so if you take derivatives to get from displacement to velocity acceleration, if you start knowing the acceleration, you can get from the acceleration to the velocity, and then from the velocity to the displacement using, you guessed it, antiderivatives. So we use derivatives to get from displacement, velocity, acceleration. We use antiderivatives to go backwards. This is one of the big ideas, and this is why I think that physics, in particular as a field, makes much more sense once you know calculus. Because if you take physics without calculus, you just learn all these formulas that are relating displacement and velocity, acceleration to each other, but you don't really know where the formulas came from. Once you know calculus, you recognize, oh, there aren't fancy formulas. All they are is taking derivatives or antiderivatives, and you're just going back and forth with derivatives and antiderivatives. Okay, so let's tackle this first problem. And we're going to do a few physics problems. And when I did physics class, I never learned any formulas. I just did derivatives and antiderivatives. And if you understand this stuff really well, you can do the same in your physics class. Although I would encourage you to listen to your physics professor. Scott Young does a great job. And I'm sure he has different ways of thinking about it than I do. Okay, so a particle is traveling in a straight line, and its velocity is given by the equation v of t equals the square root of x cubed minus 1. The first thing I'm going to do is I'm going to change that square root of x cubed. Notice the square root is a 1/2, and so this is actually x to the 3/2, and that's what a square root of x cubed means. Okay? So this is x to the 3/2 minus 1. Now, what I'm going to think about is I'm going to think about this object moving in a line. So I have some sort of line here. And we know that its velocity is always given by that equation. But what we don't know is we don't know where it's at. So the question is, where is it 4 seconds later? Well, what we have to do is we have to go from velocity to displacement. So we want to know the displacement, d of t. Well, how do we get and by the way, often people will use s's here. So D or S. Maybe I'll go ahead and use S's because that's pretty traditional. I don't like S's because my S's tend to look like 5s and that gets a little confusing. But I'm going to go with it and try to get us used to this notation. So to go from velocity to displacement, we use the antiderivative. So that means we have x to the 3/2. We will have to add 1. So 3/2 plus 1 is 5/2. and that means we put a 2/5 out in front, minus x, but then we also have to do plus a constant, because we always know that every time we take an antiderivative, we get a constant. Well, in order to figure out how far the object was 16 seconds later, we need to have some idea, we need to have some way of figuring out what this constant is. And the nice thing about physics is you have this ability to like choose your reference point, so choose where your starting point is. So where should we start? Well, there's one point that makes more sense than all the others to start. What if we start at 0? So what if we start at 0 and then wherever point we are at time equals 16, oh, I used x's for all these. I probably should have used t's because that was our variable. Sorry about that. I guess, oh, I used x's in my notes also. Well, that was a bit, I should be consistent. Whatever variable you're using here, you should use the same variable there. So if you say v of x and x or v of t and t, you should be consistent. Sorry, I wasn't very consistent. Okay, well, whenever t equals 0, if we can just put t equals 16, and whatever this point is, will be where it was located 16 seconds later. So we should probably start at 0. What does it mean to start at 0? Starting at 0 means that at time 0, our displacement is 0. So we can plug that in this equation and go. Usually, unless you have some really good reason to do otherwise, starting at the origin, starting at 0, is usually a good idea for your problem. There are occasions where it's clever to start at a different place, but most of the time starting at 0 is helpful. So what am I going to do? I'm just going to plug 0 in this equation, and I'll get 2/5 times 0 to the 5/2 minus 0 plus c equals 0, and you'll get 0 minus 0 plus c equals 0, and so c equals 0 is our constant. So that's great. That gives us our s of t equation. And so our s of t equation is now 2/5 t to the 5/2 minus t plus 0. So I don't even need to write that down. And now all I have to do is plug in 16 to find my solution. So our solution is what we get when we get t equals 16. And that tells us how far away the particle is. And so s of 16 is 2/5 times 16 to the 5/2 minus t. Okay, so this is a little bit complicated to plug in. You might want to use your calculator. I think I can do it by, I can do it without it. So notice that the square root here is 4, so I have to take 4 to the 5th power, which is 2 to the 8th power. So that's 2, 4, 8, 16, 32, 64, 128, 256. And 256 times 2 is 512. So I think I get 512 over 5 minus 16. And now, let's see, I could do 16 times 5, which is the same as 8 times 10, which would be 80. So I think I could get 512 minus 80 over 16. And let's see, 5. So I think the answer is 512 minus 100 would be 412, 432 over 5. I think that's the answer, and this will be in meters because our whole problem was in meters per second. But let me type this in the calculator to make sure I didn't mess it up. I should have done this to begin with, but oh well. 16 raised to the 5 divided by 2. Oh, I got that number. This number should have been, I got off. Times 2 divided by, I raised it to the 8th. I should have raised it to the 10th. Okay. Well, never mind. I messed the whole thing up. I'll just write down the answer. So the answer was 393.6. Well, it was a good effort, team, but I should have used the calculator to begin with. So 393.6 is what I got for my answer. You know where I messed up? I did 4 to the 5th, and so then I did 2 to the 8th. I should have done 2 to the 10th, and so I didn't count off enough 2's when I was counting off my fingers. All right, well, at any rate, let's jump over and do 3.36 and see how it goes. 3.36, we make the problem even a little bit more word problem-ish. where instead of just giving you that velocity formula, we're going to just give you some facts and let you figure out the formula. So 3.36, a ball is tossed straight up in the air. Let's go over here and draw our picture. So a ball is tossed straight up in the air, and then it turns around and comes right back down. And if the ball lands 4 seconds later, what was the initial velocity? What was the highest point the ball reached? So how are we going to think about this problem? Well, the way to think about this problem is to think of it is to take the one piece of information we know, and that is that the only force acting on the ball is acceleration due to gravity, which is 9.8, negative 9.8 meters per second squared. This is a standard. If you decide to do feet per second, your acceleration is negative 32 feet per second. I don't remember if there's a homework problem with this. Of course, you all are at home, so you're free to look things up as you need. Once we use 9.8, we always have those units there. I don't always write them down along the problem because it kind of clutters things up as I write. But we have those meters per second units. Always be cautious of units as you solve your problem. Okay, so here's A of t is negative 9.8, and then what do I want to do? I want to find out. What its velocity was, what the highest point reached. So I need to go figure out like what the distance is at different points. So I'm going to find my formulas for my velocity. My velocity t is negative 9.8 t plus a constant, and I don't know what that constant is, and I really have no way of figuring out that constant right now because the problem doesn't tell me how fast the ball is going at any point in time. Okay, but now let's take another antiderivative. So notice this was an antiderivative because we're going from acceleration to velocity. And now let's go from velocity to displacement, s of t, and I'm just going to take an antiderivative of this equation. That'll give me negative 9.8 times 1/2 t squared. So notice my t, I had to raise 1 to get a squared and divide by a 2. And then this is just a number, so let's just put c of t. And then I've got another constant. I want to write c, but c isn't really a very good one. So let's just use a different letter. I'll just pick d. It's probably a good idea for these to be different letters because they're not necessarily the same number. So anytime you're replacing a number with a letter, you shouldn't have 2 letters with the same name that could be different numbers. So I'll use a different letter for this. Okay, now let's think, are there any facts we know about this ball? The only fact I can think of is the starting point. We start right here, and I think what makes sense would be to call this 0, and so I'm going to start at s of 0 is equal to 0. So that lets me put this into this equation, and I'll be able to figure out one value. And you can already see pretty quickly what we get here. Let me go ahead and simplify this just a little bit. This is negative 4.9 t squared plus c of t plus d. And then if I put 0 in that equation, I get negative 4.9 times 0 squared plus c times 0 plus d equals 0. And this is 0 plus 0, so d equals 0 is what we get right there. Okay, so that gives me my position equation, which is pretty nice. So my position equation is oh, it's right here. So this was plus d, and that d is 0, so I can just erase it. So now this position equation right here is 100% correct. So this, well, it's not 100% correct because I don't know what c is. Okay, let's see, what else do we know? Well, we know the ball starts at 0, and it goes up, and it turns around, and it hits 0 again. Well, we knew that s of 0 equals 0, but we actually know one other piece of information. We know the time it hits here is 4, so we also know that s of 4 has to be 0. Well, that's pretty useful because now I can plug that information into this equation, and hopefully I can figure out what c is, right? Hopefully I can figure out what c is. All right, so let's go try that. And let's plug s of 4, oh, sorry. S of 4 equals 0. Let's plug that in, and what if I just come over here on this space here and plug that in? And so we've got negative 4.9 times 4 squared plus c times 4 just going to write 4c equals 0. And now I can go try to figure out what c is. This isn't too bad. I get negative 4.9 times 4 squared. What is negative 4.9 times 4? I think it's 19.6, is that right? Yeah, negative 19.6 plus 4c equals 0. 4c equals 19.6. Oh, wait. That was squared. So this should have been negative 78.4. And so this should have been 78.4. But you kind of saw where I was going. I know that when I divide that by 4, I was actually figuring out the final answer, 19.6. So we know that that c is 19.6. So now I know my velocity and my acceleration equations. So let's just come here. Let's rewrite them so we have them to look at. So I know that my position equation is negative 4.9 t squared minus 19.6 t, and I know that my velocity equation is negative 9.8 t minus 19.6. Right. Oh, hold on a second. Plus. Sorry, I got my signs off. Plus and plus. Plus makes so much more sense logically. Okay. So what I do, and this is what I did when I was in physics class as well, is I would just start attacking the problem by figuring out my equations for my velocity and my position. And once I have those equations figured out, I can now start to answer my question. So my question is, what was the initial velocity? So what is the initial velocity? Well, initial velocity is just what I get when I put 0 in this velocity equation, and that is just negative 9.8 times 0 plus 19.6. So the initial velocity is 19.6 meters per second. So 19.6 is how fast that ball had to be going initially. Okay. Finally, B, I could say, what is the highest point it's reached? Well, the highest point, notice if we think about this ball, notice it goes up and then it comes back down. What is going to be going on at the highest point? The highest point, we're going to have the derivative equal to 0. This is like finding a max. This is going back to the things we did earlier. So the derivative, which happens to be the velocity, is going to have to equal 0 at that point. So I can take my velocity and set it equal to 0. And then I would get t equals 2. So that's where the highest point is. Now I have one last thing to do on part B. And the last thing to do on part B is to figure out what is that actual height. By the way, it shouldn't be surprising that the highest point was at t equals 2, because it went up and came back down and landed 4 seconds later. The halfway point in its flight was 2 seconds, so it shouldn't be surprising that 2 was the answer. But okay, so that height is what we get when we put 2 in that S of equation, which is negative 4.9 times 2 squared plus 19.8 times 2, and I have to calculate that all out. Let's see what we get. I'm struggling with my typing. And I got 20 for my answer. 20? Is that really right? Okay, so 20 is what I got for my height. Maybe that's right. It doesn't feel... Okay, yeah, no, okay, maybe, well, okay, maybe that's right. Who knows? So 20, just not at all happy with it. Feels, I'm just surprised that it was not a decimal. Okay, if I typoed that, I'm sorry. Hopefully I got it right. I mean, 20 feels like about the right type of height, but I'm surprised that it wasn't a decimal answer. Maybe I shouldn't be surprised. Okay, so there we go. So these problems can get quite exciting, quite challenging really quickly. I'm not going to have you do very many. So what I'm going to have you do when it comes to homework is we're going to skip this 3.37 example, which by the way is lots of fun. These are examples that basically involve the same concepts I just did, but get a little bit more complex. 61 is a kind of a more complicated version of this type of problem, and I'm going to have you cut 61 and replace it with 5.9 or 59, which is kind of an easier version of this problem. 49 is a complicated version of the problem we're about to do, and I'm going to have you replace it with 47. So as you go through the problems, I'm saying do every fourth, but make sure not to do these two and do these two instead. These fit more of the types of things that I want to do. Let's start with the very last thing we have going on. And the very last thing is this graph, and that is how to make sense of a graph of an antiderivative. So this is not the graph of f. This is the graph of f prime of x. How can we take this information and figure out a graph of f of x? Well, what I would do is I would look really closely at this graph and notice a few things. One, I would separate it based on where my zeros are at. Because over here, what I notice about f prime is positive. And so if f prime is positive, that means that on this section of the graph, our function must be increasing. Resist the temptation to just follow this picture. Instead, our graph needs to be going up over here. So that means our graph needs to be kind of doing some sort of increasing on this section. Notice similarly here, f prime of x is negative because we're below the x-axis. So that means whatever my graph is doing is decreasing in this section. And again, I'm increasing in this section. Furthermore, I can see that my point of greatest increases right here. So it's going up steeper at first and then levels out. Here, it's fairly flat at 0, and then the steepest point going down is right here. So I'm going to notice that this is my steepest point, or what I call an inflection point, right? And then over here, finally, is what I get for an inflection point. Notice that this, we went from increase to decrease, so this should be a max. And this point right here should be a min, because we went from decreasing to increasing. Okay, I have these things worked out. I can kind of sketch a graph. We're not going to try to make them perfect, but we're gonna do our best. So we're going to start at f of 0 is 1. So here's 1. We're going to start right here. We're going to go up. And we're going to start going up really steep, and then we're going to level out right here at the max. Come down. Our steepest point of decrease is right here, and then level back out here. And then we hit our minimum, and then we come back up, and we start doing something like that. So here's our graph. We go up, down, and up. And now notice we're kind of not following quite the same picture as we were here, but because we're kind of off. When this is above the x-axis, this one's increasing, decreasing, and increasing. So there's a rough picture. This one isn't very good. I could do a much better job if I had more space and if I was more patient. All right, we're going to start chapter 4. We will end up cutting a couple of the sections from chapter 4, but chapter 4 is really what sets us up for Calculus 2. So I know we're at the end of the semester. I know you're kind of pushing to get everything done, and you're at home, and this is all frustrating, but let me encourage you. Don't blow off chapter 4, especially if you're going to go on to Calculus 2, because chapter 4 kind of forms the basis or the foundation upon which all of Calculus 2 is built. So good luck in your preparations, and I will see you in the next video.